Well, good morning, everyone. We're going to go ahead and get started. Hope you all enjoyed the keynotes this morning. My name's Tim Hinrichs. I'm from Open Policy Agent and Stira, and I'm your track host for the next couple of presentations. Just a reminder, we're going to have the usual setup for this talk, so 5 minutes for Q&A at the end. I'll run around with a microphone if you have questions. And don't forget to rate the session by logging into Schedge at the end of the talk. So without further ado, we have Cornelia Davis here with us today, the VP of Technology at Pivotal, and she'll be discussing Kubernetes and containers all through the lens of functional programming. So it should be pretty great.
All right, thank you so much. And just so that I make sure that I'm going to do my best for the 5 minutes of Q&A at the end, but it's 35 minutes total, right? Okay, so, right, mental note. Okay, so this is a crazy, huge room, and I was in here the other day when Zalando spoke, and they filled every seat. Thank you for coming, because I thought it was going to feel like there's 10 of us in this room that holds 1,400 people. And so I'm delighted that you're here, and I hope to make it worth your while. I'm hoping that this is going to be a really fun presentation. I do think it's kind of funny. I am going to call out to the person who's sitting in the last row on the last seat. How you doing? Big room, plenty of room. All right, so let's get started. The first thing that I want to do is introduce myself a little bit and tell you where this is coming from. So before I do that, how many people in the room would self-identify as a functional programmer? Okay, about what I expected. It looks like maybe about 10, 15%. So I think this is going to be really fun. So that's really cool. Let me tell you a little bit about myself. And I do self-identify as a functional programmer, which is why I have been so crazy, incredibly delighted with Kubernetes over the last couple of years as I've gotten involved. I, like many of you, started out I was studying computer science quite a number of years ago, 30 years ago. I think I graduated 30 years ago from university. I went to Cal State University Northridge, which is in the greater Los Angeles area. Because it was in the greater Los Angeles area, the curriculum for computer science was really focused on getting people ready for industry. And what that meant was iterative programming languages. Unfortunately, very much the same way it still is today. Maybe fortunately, maybe unfortunately, we'll get into that in a little bit more detail. The languages that I programmed a little bit in high school. I used BASIC in high school. BASIC when it still had line numbers. Some of you may never have seen that. I programmed in Pascal. Anybody else? Fortran, COBOL, Ada. Yeah, these are all the languages that I programmed in. All imperative languages. And if you don't know exactly what I mean by that, I'm going to go into a little bit more of an example. And I went into industry, and I worked for a number of years. I worked for a large aerospace company, Hughes Aircraft. And after a few years of work, I said, oh, screw this, I'm going to go back to school. And I went back to school and started a PhD. I never finished. I'm ABD, all but dissertation. And I went to Indiana University, which was interesting because it was a university out in the middle of nowhere, small town, 30,000 people in southern Indiana, very research-oriented school. And when I went there, I studied programming languages and theoretical computer science for 3 years. I did my quals in theoretical computer science. And the interesting thing when you do something like theoretical computer science and programming languages is that you learn it from a very mathematical standpoint. And it turns out the math is a lot easier with functional programming than it is iterative. And that's really the theme. That's the thing that's the undercurrent that's going to cut through this entire presentation. In fact, at Indiana University, when I was there, I think it may have changed, but when I was there, we taught Scheme as the first language that we taught to our undergraduates coming in. I was a teaching assistant while I was there, and that's the first language we taught them. And there were some really interesting things that I'll maybe touch upon as we go through the presentation. I obviously can't get too far away from my laptop. There we go. At Pivotal, I work on product strategy. I've been with Pivotal since the spinoff, so I worked on Cloud Foundry for a number of years. I worked on our cloud caching product, and for about the last 2 years, I've been working on our Pivotal Container Service product, which is our Kubernetes product. I identified as a dev, but since working at Pivotal and working with customers on the platform, I have become an operations person as well. And more recently, I have just finished this book. The print copies started shipping the day before yesterday. So I just finished it. And if you're interested, there's a discount code there for 40%. I'll put this up again at the end, the discount code, if you're interested. The book is an architectural book, so it's all about cloud-native patterns, things like scale out, statelessness, retry storms, circuit breakers, service discovery, all that stuff, but very much from a focus of why are you doing these patterns? The patterns themselves aren't that hard. But if you understand the why behind them, you'll be able to use them a lot more effectively. So that's what the book is about. All right, without further ado, let's jump into it. And that's a blank screen. And yes, I remember where we're going. So when I started programming, I actually started programming embedded systems. And what we had in embedded systems was we had single-threaded processes running on a single processor on a single machine. That was it. No distributed systems whatsoever. And then we started to evolve and we started to have multiple processors. I even remember working on an embedded system once where we had 2 processors and we actually had out on the whiteboard where the communication points were going to be, and we actually timed how long it was going to take to run a certain piece of code over on this processor so that we could then hand over to this other processor that was going to do a number of things. I see a couple of people nodding, so this is somewhat familiar. So we started having multi-processors or maybe even multi-threading. So we added that. Then we started having multi-threading, and then we added multiple processors. And now we're all distributed systems programmers. Agreed? Right? The internet happened, and we all program distributed systems. Part of our logic runs in the browser, part of it runs on the mid-tier, which used to be a single machine, but now is a whole bunch of different machines. That's one of the things that characterizes the cloud. So we're all distributed systems programmers now. 30 years ago, that was just very niche. So what has happened to programming languages over the course of this? Well, in the beginning, I even did a little bit of assembly programming to really optimize all of the processing that you could do on that single processor. But arguably, when you start going into multiple threads, programming in assembly gets really hard. So you have to use some higher level languages that maybe know some things about threads and those types of things. So you see a whole host of languages here. What is interesting is that as we've all become distributed systems programmers, we've started to see popularity emerge for a new category of languages. And those are the functional languages. So the earlier languages were all imperative languages, and that's what, again, I learned about 30 years ago. But these newer languages fall into the category of functional languages. Okay, so that's for functional programming. And there's a couple of reasons for that, but I'll go into that in just a moment. I want to show you an example. So for those of you who really are thinking like, okay, vaguely I understand the difference between imperative and functional, let me give you a little bit of a review. And I want to do so with an example. So when I initially started doing some of this work, my son, who graduated with a degree in computer science, I am so happy. He was doing a class in bioinformatics. And one of the projects that he needed to work on, they were taking the human genome and they were doing some sequencing on that. And what they needed to do was take the genome and break it down into segments, and then they process each one of the segments. Of course, they're doing it in parallel. And then they merged the results together. There was an algorithm that they were doing there. And so the first step was to take this really long string and break it down into segments. But if the segments were too small, then the processing that happened within a single segment wasn't really meaningful anymore. There wasn't enough data. So after breaking into smaller segments, he wrote an algorithm to merge together segments that were too small. So what you see here is you see the ranges on segments. The first segment is 5 long, 0 through 5 non-inclusive, then 5 through 17, 17 through 20, and so on. And so what we want to do is we want to merge this together into segments that have a minimum size. Well, actually, initially, and so that's what we're going to do here. Sorry, I'm stealing my thunder. So this is going to be the output. 0 through 5 is too small, 17 through 20 is too small, and we're going to merge them together. So let's look at a couple of different ways of doing that. The first thing that my son did was he wrote it in Python. And he wrote it, despite my best efforts, he wrote it in an iterative style. And rather than stepping through the code, let me show you pictorially what this algorithm effectively does. Starts out with the first array of segments, and it does a scan. It finds one that is too short, and it merges it into the next, moves the cursor over, finds another one that's too short, merges it in, moves the cursor over, and now the cursor, the counter, is one beyond the end, and that was the exit criteria for the loop. And you get this answer. But you know what? There's actually a bug in that algorithm, which gets me to the point of some of the characteristics, the hallmarks of iterative programs. They're sequential. You control every step. Remember that, because that's one of the important things that when I start to characterize it in the Kubernetes lens, that you no longer control every step. That's one of the big differences. So with imperative, you control every step, and you have side effects. You've got variables. And what you end up with is hairy edge cases, and it's difficult to parallelize because you have shared state. So how are you going to coordinate all of these different threads that are working together on shared state? So it's very difficult to parallelize. And in fact, that algorithm that I just showed you a moment ago had a bug in it. It worked out because the last segment happened to be long enough. If the last segment in the end had been too short, we would have had an error in that program. Okay, so it would have crashed. So instead, if we take that approach in a functional style, sorry, I'm double clicking. Here I've written the same algorithm in Scheme. And what you see here is that there are no side effects. It's entirely immutable. And the way that it works is very interesting. We're going to start with the same thing. And what we do is we peel off in Scheme or Lisp, we call it the car. You haven't done your Scheme or Lisp in a long time. We peel off the head of the list. Then we make a recursive call on the rest of the list. And we trust that we're going to get the right answer. Doesn't that sound a little bit like inductive proofs? Assume n, then you can prove n plus 1. So we make the recursive call, we assume we're getting back the list, and then we finish our processing, where we do a merge and we get the final result. So that is a fundamentally different approach. There's no bugs in this particular algorithm. Now, the hallmarks of functional programming, then, are that they're declarative. You are not doing every step in the sequence yourself. You're taking this leap of faith and saying, the recursive call is going to give me something back, and I'm not worried about how it does it. And so that's a much more declarative approach. There's no side effects. So yes, there is a set bang in Scheme. Don't use it. And you're generally doing recursion, and you'll see where these themes come in. And what that ends up is that it's easier to program in a way that allows for parallelization. You have far fewer hairy edge cases, and it's provably correct and allows you to do certain optimizations, like partial evaluation and lazy evaluation. Not going to talk more about that because we want to get onto the Kubernetes stuff. All right. Now, this is some work that I've been doing with a colleague, an industry colleague of mine, who many of you probably know by name. It's Gene Kim, who's one of the co-authors of the Phoenix project. And he has been going through this transition from it being an iterative programmer to a functional programmer. And this is a quote that I got from him, which is he had a program that he wrote that took 3,000 lines of Objective-C, he rewrote it into 1,500 lines of TypeScript, and then eventually into 500 lines of Clojure, and he absolutely adores Clojure. I'll say more about that transition that he went through at the very end of the presentation. So it allows you to write more compact code. The real point here is that this iterative model and the functional model, they're two different models, not only of programming, but also of the way that we think. And that's the question that I'm going to pose, is what's the model that we're going to use to reason with? For iterative versus functional programming, to sum it up, on the left-hand side, we're doing iterative, on the right-hand side, declarative. Left-hand side, mutable state to immutable state, and we'll see how that comes up again. Looping to recursion. And it's not really functional programming, but it is a modern programming practice that shows up in the Kubernetes space that I want to talk about, which is the difference between libraries compiled in and something like aspect-oriented programming and dependency injection. So as much as I love this woman who is a like 80-year-old computer programmer, rock star, as much as I love her, there are certain things, our systems have gotten so complex that we don't want the human programmer to be doing all of the reasoning anymore. We want to allow our software to do some of that reasoning for us. If you remember the transition, if I had to write my programs in assembly and that was the model that I thought in, I wouldn't be able to solve the same level of complexity in those problems. All right, so let's shift now. Let's turn our view. I'm just looking at the time. Great. The whole point here is that with distributed systems, we can no longer reason about every detail that we used to reason about. Our systems are just too complex. So we've shifted the model. And that's one of the most powerful things in Kubernetes. Yes, it's a container orchestrator. That's great. It knows how to schedule. But it's all of the other things that it does that I'm going to touch upon in this talk that make it even more powerful. All right, so if we now turn to systems programming, I want to go through. Now, when I say systems programming, I'm not talking about the code in my applications. I'm actually talking about things like my actual application topology, my application deployments, my application upgrades, my application security, those types of things. That's what I mean by systems programming. So it's kind of that next level up. So in the olden days, what we were able to do was we used things like automation. And we used languages like Bash and Puppet and Chef and Ansible and Salt. Those are all iterative programming languages, systems programming languages. But as our systems have gotten more complex, so these are imperative, as those systems have gotten more complex and I have more nodes in there, what are some of the languages that are emerging, the languages? Well, I come from Cloud Foundry. So Cloud Foundry has embraced that, in large part because Cloud Foundry was incubated by a handful of folks that came over from Google, who had worked with Google Borg before. Kubernetes, of course, and that's what we're going to talk about today, and then another subsystem that's within Cloud Foundry called Bosch, which has the same DNA as Cloud Foundry, PaaS, and as Kubernetes. Some of the same patterns that we're going to talk about here. And so that's what I'm calling functional systems programming. So remember that previous slide, let me build that out. What we're going to look at is on the imperative side, we have scripted deployments. Now we have declarative deployments. Everybody's probably pretty familiar with that now. Hopefully you're not just doing a kubectl run. You are using manifests and doing declarative manifest and declarative deployments. In the olden days, we might have SSH'd into a box. Never anymore. We've got Weaveworks, for example, down there that has on its poster behind their booth, GitOps. So they're talking about doing all of this via Git and immutable infrastructure. And I'll drill into each one of these. Long-running contexts versus ephemeral containers. I'm going to show you something that might surprise you a little bit around ephemeral containers in just a moment. And then finally, we're moving from kind of the old way of doing middleware to sidecars. So instead of having an entire platform, we're even doing that within Cloud Foundry. Cloud Foundry used to be a little bit more middleware-like. It had everything baked into that platform. Now we're starting to put some of that capability into Sidecars, and I'll talk about how that works. So again, it's all about the model. Okay, so let's jump into each one of those. This one I'm going to go through fairly quickly because I think it's pretty familiar to all of you in this Kubernetes space. So of course, here I have my Kubernetes nodes. And when I want to do a deployment of my application, no longer do I say, stand up this node, deploy the app here, stand up this node, deploy the app here, even with imperative automation. What I simply say is, here's my topology. This is it. Make it so. And that application gets deployed. There we go. The animations are going super slow, so I never know. And it does that deployment. So notice that you didn't have to make those decisions, and that's where the scheduling comes in. But it's not only the scheduling, because what I want to say is that it goes beyond scheduling. And actually, if you think about it, the equivalent of the scheme interpreter that decided when it was going to execute that recursive call and how far down the recursive call it's going to go before it stops, gets down to a base case. So things in functional languages like lazy evaluation that say, you know what? I'm going to defer the execution of this entire stack of recursive calls until I actually need them. Instead of doing them when you say you want me to do them, I know better. I can do an optimization for you. So that is what Kubernetes is doing, so that when you, and with compliance, there's an example here with daemon sets. Of course, it does that on the nodes as well. The whole notion there is that the control loop is the place where you can do optimizations. And because you are following functional principles, like immutability, like declarative configurations, it allows you to put more intelligence into the reconciliation loops that are in Kubernetes. And notice that I said loops. For some of you who are new to Kubernetes, you might be just thinking about the replica set controller, but there's a lot of reconciliation loops in Kubernetes. I sometimes like to say that Kubernetes is just a system of a whole bunch of, it's a registry of a whole bunch of infinite loops that are all running and doing reconciliation. Okay, that's really at the core of the architecture. And that's really the point here. And notice here that I also had a node go away. And we can, in fact, even use control loops to recover those nodes. We do that today with PKS using Bosch. And you saw Joe Beda talk in the keynote yesterday about cluster API. Same basic idea, reconciliation loops for the clusters themselves. And of course, here's my point, is that you have multiple reconciliation loops and they're all independent. Okay, so this is a little bit like functional programming. I'm going to go through this very quickly. I already talked about this. You've got the base case. And then that recursive call is a little bit of a leap of faith. When you make the recursive call, you don't worry about how it's actually getting the answer. You just trust that it's getting the right answer. And then you just go on your way. All right, so that was declarative. Let's now move on to immutable infrastructure. So there's a couple of things that are really interesting about immutable infrastructure. So in the olden days, we certainly had pipelines. So that's the first step. And we've had pipelines for a long time, so that we aren't having a human being sitting at a console saying, oh, let me do an AWS get machine, and then I'm going to do I'm going to SSH into the box, and I'm going to start executing some commands, apt gets, and things like that. I at least have all of that in a pipeline, which, by the way, is imperative. So I've got provision and configure, and then deploy, and then configure my app. So provision the infrastructure, configure the infrastructure, deploy the app, configure the app. And notice that I've got the little Git icons in there, so my configurations are all source code controlled, right? We're all doing that. So if we take a look at the way that we've been doing things, there's still challenges that remain. And I won't go into a lot of details, but one of those that I have seen in customer sites over and over is that it's slow to provision a new VM. It's slow to provision a new VM. Remember I said, and actually Tim said when he introduced this, that we're going to look at some of the principles of Kubernetes and containers from a functional lens, and immutability is one of those things. Well, the fact that immutability is really important for repeatability, right? Everything comes from Git, everything is repeatable. But what happens is if there's a step in your pipeline that takes too long, then we start putting in shortcuts. So I worked with a customer once who discovered that they had all sorts of shortcuts where they actually weren't starting from scratch. They were leaving VMs in place, and so they were getting configuration drift all over the place. So even with that pipeline-driven process, that's one of the problems. So we end up with snowflakes. And then there's super complex dependencies, and we aren't doing a good job capturing those because we don't have a declarative way of capturing those. And I'll get back to that in just a moment. So if we go back to this picture then, the first thing that I want to do is I want to take the first two steps, and I will totally admit that this has a bias hat on it because I come from a platform vendor. And we've seen the value of platforms. Now, this is a friendly audience because we're all here talking about a platform for building platforms, right? So everybody buys that platforms help us here. So what we want to do is we want to take the first couple of steps and push those down into a configured platform, like Kubernetes. That still leaves the deploy and configure step on the right-hand side. So what we do now is for that deploy and configure, we can start leveraging containers. It's now going to take milliseconds instead of 5 minutes. And so some of those shortcuts that I talked about before, you no longer need those. So that's one of the advantages. So we can take that process then, and of course we can do that we have multiple instances of apps now. That's one of the characteristics of cloud native applications. So I want to be able to do all of that bundling and configuration once so that I can scale out my number of pods, scale in my number of pods, move pods when I'm doing some type of a CVE vulnerability patching or something like that. And so if I take that now and I move it up here and I say, great, I'm going to do that whole step, and I'm going to do it earlier in the process, and I'm going to leverage things like Helm, Git, and image repositories like Harbor. I can do all of that stuff that I used to do at deployment time, I can do it before. And in the DevOps community, and I spend a lot of time in the DevOps community, we talk about shift left. So what this means is that I can do all of this very early on in my development cycle so that deployments then are a no-brainer. And easy deployments are an important part of writing cloud-native software and cloud-native practices. So you might be thinking, well, what does all of that have to do with imperative and functional models? Okay, you're telling me about Kubernetes, but come on, bring this back to functional models. So let's take a look at that. When we did state the previous way, remember there's the counter there, the way that worked was that we were constantly moving state around and immuting state and all of that stuff. And in the end, we really have no idea. We have the final answer, but we have no idea how we arrived at that final answer because all of that history is lost. If instead, on the imperative side, we end up looking at things, and so here's the point, is how do you prove the correctness? Remember I said that that algorithm had a bug in it? So if you're allowing for side effects, how do you ever prove the correctness of a piece of software? It's very difficult, if not impossible. So other influences plus a state-based, mutation-based algorithm, and you end up, you can't prove the correctness of that. If, on the other hand, you take a functional approach, this is what your functional execution looks like. Remember, it's a whole bunch of recursive calls. And each one of the frames on the stack are immutable frames. And then to actually achieve the answer, you're just playing through that call stack to get the answer. So the call stack, and again, it's just going, my animations aren't usually that slow. I don't know what's going on. The frames are immutable. And what we're going to do is play through the call stack to get the final answer. Okay, so that is, you see at least at a gut level, the kind of parallels that are going on there. Okay, so, okay, there's a funky animation. Obviously didn't triple check these last night. Sorry. And so if you draw that parallel, the container images are a bit like your stack frames. And your interpreter, Kubernetes, the controller, is a little bit like the execution through the call stack. So, great, thank you. All right, so let me push forward. There's another place that we're seeing this pattern. I'm just going to build out the slide very quickly. And it has to do with the way that we're doing eventing and doing things like immutable event logs. So event sourcing in Kafka, where you have all sorts of different event sources that are putting things into this event store. So a legacy store is adding change events into the event store. And then each one of the consumers, and again, those events are sequenced and immutable, just like the call stack we talked about a moment ago. And then we can play through each one of those things to get to to other sources. So there's a whole nother talk there. All right, let me quickly go through these last two things, and that is ephemeral containers. Now, this is a story that I can tell very quickly. Everybody here is familiar with what this picture is. We've got a host. On the host is the kernel operating system. Running inside of the container is a root file system, some other runtime stuff, and then finally the application on top. And I've got multiple containers. I'm just showing one here for simplicity. So we know that these containers are immutable and that we have container images that we can spin up. Let me share with you a super cool use case about this. And here's the thing. Malware. A bad actor comes in and drops malware into my system. And we know that a lot of the breaches out there are caused from malware that went undetected for months at a time. And the bad actor goes away, and so we can't detect the bad actor anymore, but the malware is still there. Okay, there we go. Bad actor goes away. So how do containers help you with this? So again, remember the difference was long-running state versus immutable ephemeral containers. Well, here's what one of our customers at Cloud Foundry does, because we're container-based, not quite Kubernetes-based yet, because we predate Kubernetes, but it's container-based. What they do is proactively, without knowing whether there's malware or not, they do this. They, on a periodic basis, just throw away the container and stand up a new one. If there was malware on it, it's gone now. If there was no malware on it, cool, there's still no malware on it. And they not only do that at the container level, but they also do it at the host level. So they throw away the host, stand up a new host, so if there was malware on it, it's gone, and the container is stood up and it's clean. So they do this proactively, they repave their environment, and they're able to do this because of the containers that they have. I'm suggesting that you do that very often. This particular customer, and it's Wells Fargo, because they talk about it very publicly, they do it every 3 days. Lance wants to do it so that he does it every single day. He doesn't want a container in his infrastructure to live longer than a day, which is super cool. All right, I have 1 minute left, so let me wrap it up, and I will stick around afterward. We can go out in the hallway and I'll answer questions there. Finally, on the sidecars thing, I'm going to flip through this very, very quickly. And that is, let me skip through this slide, because I really just want to talk about, here we've got our containers. And now what we want to do is, without actually having to insert something into the code itself, what we want to do is we want to take advantage of cross-cutting concerns, like routing, like auditing, like certain security things. And we do that, of course, with sidecars. And there's personas here that care about that. So this is, for example, your auditor that cares about that. The way that we're going to do that, of course, is in the pod. So a pod, this is why pods have more than one container in them, or certainly one of the great use cases, is that I can have my application container and I can have my sidecar. Okay? So that's that. And of course, we can do that using things like daemon sets. We can do that at the host level as well. And that's what I'm showing you in this picture. Okay. And I see that I'm 20 seconds over. I'm going to leave you, if you'll permit me, 30 more seconds. I just want to share one final thought. And that is, sorry. Yes, this is the final thought that I'm going to leave you with. Is if we take a look and we go all the way back to the functional programming metaphor, if you remember, those things were declarative, and at the top here we see declarative deployments. Well, that was a hallmark of functional programming. We had immutability, well, immutable infrastructure. Immutability is a hallmark of functional programming. Ephemeral containers that you can use that you can then recreate and compose, that is where the parallel is to recursive. And then sidecars, they look an awful lot like aspect-oriented programming. So I hope that was kind of a fun look between functional programming and iterative programming and kind of the parallels into our Kubernetes world. I'm going to go ahead and put up the last slide while I step off the stage and start to maybe answer a few questions. Apologies for not having time. Thanks so much. Have a great day.